meeting, then what happens? Yeah, now it starts. Okay.
I'm extremely sorry.
No, it's fine, it's fine, it's fine. Perfect. These things happen all the time. Okay, so we were talking about conjugacy as another way of partitioning a group. Two elements are called conjugate to each other. G2 and G1 are conjugate to each other. If, well, there exists an element G in the group such that G2 is G, G1, G inverse. And it's important and a nice homework to check that this really is an equivalence relation. That it satisfies all the three properties that we listed. Okay, and as in every equivalence relation, if you collect all the elements which are equivalent to each other, you are going to get what is called an equivalence class. So the equivalence class of an element G is defined to be all the elements G prime belonging to capital G, such that there is some G bar in the group somewhere, so that G prime is G bar G, G bar inverse. That is, G prime is conjugate to G. Now, of course, it's easy to see that if G were the identity, then no matter what G bar you chose, G bar will always jump across G because identity commutes with everything and kill the G bar inverse. So the only element which is conjugate to the identity element is the identity element. So in every group, the identity element is always in a class by its own. Okay. And if you have an abelian group where every element commutes, then of course G bar G, G bar inverse will be the same as G, G bar inverse will be the same as G. So in an abelian group, not only the identity, every element is in a class of its own. So these are two special cases. For every group, the identity is always in a class by its own. In an abelian group, all elements are in a single class of their own. In a general non-abelian group, you will have different sizes for classes. By the way, this again does not mean that if you have a non-abelian group, the only element which can be in a class of its own is the identity. There may be other elements as well. I will just give you an example or a couple of examples of that. So, well, this IG is a notation that we will come to very soon. It's called the inner automorphism. That's just a big sounding name. But IG is just a map which carries G prime to G, G prime, G inverse. Okay. So that essentially says that if you apply IG on a given element G prime for all the elements in the group, that is, if G runs over all the elements of the group and you keep on applying IG1, IG2, IG3 or G prime, and if you do it for all the elements G1, G2, G3, etc. in the group, then you will ultimately end up collecting all the elements of the group which are conjugate to G prime. That is, you are going to get the G prime's conjugacy class. So here what I've done is I've just taken our example of the set of all symmetries of an equilateral triangle, which remember we are calling S3, right? Because we saw that there is no difference between that group and the group of permutation of three objects. So we are just giving it the standard name S3, just for brevity. And for that, if you just looked up his multiplication table, this is not the multiplication table, of course. What we are saying is here IE is acting on E, IA is acting on E, AB, and so on. And it's easy to see that this is what is going to come out ultimately. Again, this table is something which you don't have to memorize, but you can easily reproduce it from the standard multiplication table. Just to illustrate, let's take this element. This is actually IC acting on A. So that means CAC inverse. Now what is C inverse? C inverse is whatever undoes a reflection along the median C, that's actually C itself. Remember, any reflection, if you do it twice, you are going to get back the identity. So C inverse is nothing but CAC. So if you just go back to the multiplication table or just draw your own triangle and check what happens if you do CAC, you will easily check the CAC comes out to B. So if you look down the column here, this is actually IE, IA, IB, etc. done on E. This column is the same thing done on A and so on. So these are all the elements which are conjugate to E, which of course is only E. These are all the elements which are conjugate to A. So as you can see, A, B, C are all conjugate to A. So the conjugacy class of A is ABC, and no surprises, if A is conjugate to B, so then B is conjugate to A and so on. So B also has the same conjugacy class as A. So does C. So ABC, if you look at the class of elements, take all of the elements that are there in these columns, you will see is A, B, and C are in the same class. D is in a class with F, and of course F is in a class with D. The conjugacy classes here, there are three conjugacy classes, one element conjugacy class, which is E, another two element conjugacy class, D and F. The third conjugacy class here happens to have three elements, that's A, B, and C. Okay. Is this clear to everybody? That is how you form the conjugacy classes. Of course, a question like that essentially means that if somebody has a doubt about this, please ask. Of course, you have to actually carry out the calculation yourself to be convinced that this is really correct. But I hope you have got the point as to how to calculate this. So in this case, what you see is that the identity is in a group of its own, conjugacy class of its own. The two rotations, D and F, two non-trivial rotations, are in a class of their own. And the three reflections, A, B, C, are in a class of their own. Okay? And that's not an accident. But it's not true that all reflections will always be in a class of their own. Just to illustrate that, let me take a look at another set of symmetries quickly. This is again another symmetry group, which is going to be very important, which is quite important in physics. It's a symmetry group of a square. And there are more elements here. What are the elements? Well, you do nothing. That's a symmetry operation, right? Then you rotate by pi by 2. If you rotate this by 90 degrees, of course, that's a symmetry operation. Rotating by 180 degrees, that's another symmetry operation. And then if you rotate by 270 degrees, that's another symmetry operation. So you have three non-trivial rotations. You actually have four rotations. E, of course, is a rotation through 0 degrees. In addition, of course, there are reflections. Reflection along the median lines like this, A and B. And there are two more reflections, which are again obvious. They are reflections along the diagonal lines. These are also symmetries. So the set of symmetries of a square, or at least set of symmetries of a square, keeping it in the plane, is a set of 8 elements. They form a group of their own. And you can, of course, play the same game that we did earlier with a triangle and write down this multiplication table and all that. I'm not going to do that, but you can do that if you want to. And the important thing is you can easily check the conjugacy classes, and the conjugacy classes will turn out to be this. Identity will be in a class of its own, as always. G, which is a 180 degree rotation, will also be in a class of its own. F and H, the 90 degree and 270 degree rotation, will be in a class of their own. The AB reflections will be in a class. CD reflections will be in a class. So here you have 5 classes with elements 1, 1, 2, 2, 2 each. Now again, this is something of which of course you may not be able to understand right now because you have to work out the conjugacy relations. But let me tell you a quick way to understand this as far as rotations and reflections are concerned. In most of our symmetry operations, rotations and reflections will play a big role. And there, the basic rule is very simple. Rotations are in the same class if they are through the same angle. Which is why identity, which is through 0 degrees, is of course in its own class. Well, 180 degrees, G, that's the only rotation that's there. That's in its own class. Well, C, G, F and H, they are 90 degree and 270 degree, but actually 270 degree is also a rotation through 90 degrees about an inverted axis. That's why they are in the same class. Now, reflections are in the same class if there is an operation which changes the plane of reflection, or in this case, a line of reflection, because we are in 2 dimensions, to one to another. So A and B are in the same class simply because there's a rotation which changes the line A into the line B. But A and C are not in the same class because a 45 degree rotation, which will change A into C, is not a symmetry element. So that is why, despite the fact that A, B, C, and D are all rotations, A and B are in a class of their own, C and D are in a class of their own. This conjugacy class structure is going to be very important later on, because we will see that there's a connection between conjugacy classes on the one hand and irreducible representations of a group in the other, and those are really the basic building blocks which we are going to study in this course. And very quickly, conjugacy classes for the permutation group. This is going to be very important for many purposes, especially one of the lectures later. Let me just point out what the conjugacy classes will look like. So given two permutations pi and sigma, the conjugate permutation to pi is sigma pi sigma inverse. What does it do? Well, you ask what does it do to I? Well, what does it do to sigma I? That's easy. If you look at what it does to sigma I, sigma inverse of course undoes sigma, it gives you back I. Then pi goes and acts on it, you get pi acting on I. And finally sigma acts on it. There's a typo here, this should not be pi sigma, it should be sigma pi I. So this is wrong. This thing is written here. It should be sigma of pi I. So it maps sigma I to sigma of pi I. Now why is that interesting? Okay, again, this typo, of course, this is a copy-paste error, so that's why the typo has progressed here as well. This is sigma pi I, not pi sigma I. It's easy to see that that's going to happen, right? Sigma inverse cancels sigma, pi acts on I, so there's pi here and then sigma. The permutations do not necessarily commute, so pi sigma and sigma pi are quite different. So this is really wrong in general. It should be sigma acting on pi I. But what is this going to mean? Essentially means something like this. Suppose you have two different permutations, pi, which has this particular cycle structure, and sigma, which has some cycle structure. I'm not really interested in that so much. Remember, I'm looking for elements which are conjugate to pi. Pi has a cycle structure, 5 elements in a cycle and 3 elements in another cycle. Now, what is sigma pi sigma inverse going to do? Well, it's going to essentially, oops, there's a, sorry, I must have messed up my typing a bit. So let me just switch to my pad and just ask, let's ask the same question here. Oops. So let's just write down some sigma, some pi. Maybe change the color. Which takes so maybe this takes 1, 2, 3, 4, 5, 7 in this cycle, and then I missed out 6, 9, 8, let's say, and sigma. Okay, maybe I think I got the right thing. I just read it wrong. Okay, let's just see. Yeah, I think this is right anyway. Sorry about that. This is pi is this particular cycle 1, 3, 4, 6, 2, and 5, 8, 7. That is 1, 5 cycle, 1 cycle. So what does sigma pi sigma inverse do? It essentially moves sigma 1 to sigma 3. Just read this as sigma pi I. So pi moves 1 to 3, sigma pi sigma inverse moves sigma 1 to sigma 3, sigma 3 to sigma 4, sigma 4 to sigma 6, and so on. So that cycle will simply look like this. Sigma 1, sigma 3, sigma 4. So I just take, instead of 1, I put in sigma 1. Instead of 3, I put in sigma 3. Instead of 4, I put in sigma 4, and so on. That's all that is going to do. And similarly, this 5, 8, 7 cycle will become sigma 5, going to sigma 8, going to sigma 7, going back to sigma 5. And if I just look at what is sigma 1 from this, sigma 1 is simply 4. So I put that in, and I can just fill this up and get the whole thing written down. But what is critically important here? The details of what goes where is not that important. What is critically important is there is a connection that you can immediately see between pi and sigma pi sigma inverse. Can anybody tell me what that connection is? Something is identical between pi and sigma pi sigma inverse, which is?
They are basically both same, just rearranged.
No, they are not the same. That's not really true. This one takes 1 to 3, okay? And 3 to 4, 4 to 6. 62. Are you saying this is exactly the same? Might even be by chance, but I'm not really sure.
Excuse me, sir.
Yeah. Yes.
Sir, I think
Well,
the cycles are same in both cases.
yeah. What is I? Okay. By the way, I will have to check carefully whether the previous answer was correct by accident. That is, might even turn out. No, it's not, because 41326 is not the same cycle as 13462, right? By chance they have the same elements, but 413. If you just look at this says 4 goes to 1, right? Here 4 goes to 6, so they're entirely different permutations. But the next answer was perfectly right. You had 5 cycle, a 5 cycle and a 3 cycle. Here also you have to have a 5 cycle and a 3 cycle.
3 cycles.
The cycle structure has to be exactly the same. Okay, and you can easily check that if you have two permutations with exactly the same cycle structure, can always find a sigma such that it will convert one to the other. That is, by doing sigma by sigma inverse, one cycle, a permutation with a particular cycle structure can always be made into another permutation with the same cycle structure. Okay, so this is a general statement. Any two permutations with the same cycle structure must belong to the same conjugacy class. What that means is, this is why cycle structure is so important. If you want to identify the conjugacy classes, all you do is look at, do they have the same cycle structure or not? And what actually tells you, what is the cycle structure here? It says that this is a 3 cycle and a 5 cycle, right? You have 8 elements, and 5 plus 3 gives you 8. So basically, you are breaking up the number 8 into 5 plus 3. That's all there is to it. And all different ways of forming a 5 cycle and 3 cycle will give you the same conjugacy class. Give you different elements. This pi element and this sigma element, this sigma by sigma inverse are two different permutations, but they have exactly the same conjugacy class. They are in the same conjugacy class. So, basically, there's a one-to-one correspondence between conjugacy classes and the cycle structure. And cycle structure is simply nothing but how many ways can you break up the number n into integers which add up to n. That's called, that in the language of number theory is partitions of n. So I will just illustrate, this is a table here. For S5, this is a particular thing that I'm writing for S5. We can have the following cycle structure, which has a one-to-one correspondence between the partitions of the number 5 and with conjugacy classes. So how many ways can you break up the number 5? You can break it up, of course, into 5, which will give you 1, 2, 3, 4, 5 as one example. So 5 elements all in the same cycle. Of course, this is not the only possibility. 1, 2, 3, 4, 5 all in the same cycle. There could be more. Say 1, 3, 2, 4, 5 could be a different permutation. Not 1, 2, 3, 4, 5. But that would be conjugate to 1, 2, 3, 4, 5. So this thing that I've written in blue here is just one example of an element from the conjugacy class. There will be more in general. Okay. So, well, if you go down this column, 5 can be broken up as 5, then as 4 plus 1, then as 3 plus 2, then as 3 plus 1 plus 1, then as 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and 5 ones, and there's a typo here once again. This one, 1, 2, 3, 4, 5. This should really read 1, 2, 3 in a cycle of its own, 4 in a cycle of its own, 5 in a cycle of its own. So it really should be 1, 2, 3. What I've written here is actually the same as a 2, 1, 1, 1 cycle, which is actually conjugate to this cycle here. Okay. But what I really mean is a cycle 1 in a cycle on its own, that is 1 doesn't move, 2 doesn't move, 3 doesn't move, 4 doesn't move, 5 doesn't move. Okay, so these are different examples of elements in a conjugacy class. And these different ways, 1, 2, 3, 4, 5, 6, 7 different ways of splitting up the number 5 into non-negative integers is actually what is called the partitions of 5. It's also the number of conjugacy classes. And each of these here are just examples. Now, in addition to this, I have something in red on this side. I will not talk a lot about these things, but these are basically tools which people use to discuss both conjugacy classes of SM, also various different ways of doing combinatorics. So these are important both in group theory and in ordinary number theory when we do combinatorics of numbers. Also, as will definitely be discussed in a later lecture, as I can see from the schedule.
Hello. Excuse me, sir.
Yeah, go ahead.
Sir, I have a question. Do you mean that the number of possible cycle structure is equal to the conjugacy class of the group?
I think I'm not sure whether that language is what I would use. What I would say is that given cycle structure corresponds to a conjugacy class. So different kinds of cycle, number of different cycle structures lead to different conjugacy classes.
Okay.
So there are seven different partitions of the number 5. These gives rise to 7 possible cycle structures, each correspond to a conjugacy class.
Okay. So
of which the last one is wrong. Please don't get confused by the last one. There's a typo here. And by the way, go ahead.
For this S5, we will have this 7 conjugacy classes.
Yeah,
according
S5
to
has 120 elements, right?
Okay.
Because 5 factorial, and they will break up into 7 conjugacy classes. Okay.
Okay.
And
thank you.
What I've shown in blue is just one example of an element for each conjugacy class. It's an interesting combinatoric problem which almost everybody here should have no difficulty with in figuring out how many elements each of these conjugacy classes have. For example, this one is the easiest. This has only one element. Of course, not this one. This one is wrongly written. But yeah, go ahead. Somebody is saying something. Very.
Like we are breaking here 5 in 4 plus 1. So can we break it as a 1 plus 4 also?
Well, if you count it, you don't count 1 plus 4 as different from 4 plus 1 because that gives you the same cycle structure. Okay. That is, if you wrote the 5 in front and wrote 1, 2, 3, 4 after that, will it really give you a different permutation? It won't, right? Is that understandable? So that's why I don't write 1 plus 4. And that's actually the reason why when we write this, just to ensure that we do not overcount the partitions, you don't count the same partition twice, you adopt the convention that the numbers will be strictly non-increasing. That is, you wrote, for example, here I wrote this as 2 plus 2 plus 1. The numbers don't increase, so I don't write this as 2 plus 1 plus 2 or 1 plus 2 plus 2. Okay? That if I wrote that way, I would actually get the same cycle, just written different.
Sir, I do have a question.
Yeah, go ahead.
Sir, this number when you are saying, is it possible that we can give a formula for this? Like for 5, we are getting the 7. Like for S3, we are getting.
It is. Okay. You need to know a bit more of number theory for that. Number of partitions of an integer is a very important number theoretical thing. You can.
Okay, I get it, sir. I will look into that.
Yeah. And moreover, the number of elements in every conjugacy class, you can actually figure it out by using elementary combinatorics. And the diagram that I was talking about, well, this diagram is, if you look at it, these are called Young diagrams, simply after the fellow who talked about them the first time. And they are the templates for what are called Young tableaus, which is going to be discussed later on in this workshop. Well, you can easily figure out the rules for writing down the diagrams. This 5, just put 5 in a row. 4 plus 1, 4, 1. 3 plus 2, that's 3 and 2. That's it. So it looks like it's something very trivial. You just are writing down these numbers here. Instead of writing down the numbers, you're just putting down squares. And that's true. That's just the way in which you write a Young diagram corresponding to a conjugacy class. But then you have, once you have a diagram, you can do more things with it. You can put numbers inside the boxes and you can use that to figure out various things like dimensions of representations and stuff like that. I'm not going to talk a lot about Young diagrams and tableaus because there will be other speakers who will talk about them. But I just wanted to point out that Young diagrams are really just ways of denoting conjugacy classes. And just to give away the next lecture's topics a bit, conjugacy classes are related to representations in a very, something called irreducible representations, things which are basic building blocks of representation theory in a big way. And that's why we sort of talk of them together. Okay, let's move on from this, because frankly, I'm not going, this structure for SN is a huge topic that would take me at least 4 or 5 classes to cover if I wanted to do it in full. I will just leave you with this basic idea that if you can easily think about the conjugacy classes just in terms of the ways of breaking up an integer into pieces. Okay, now we come to a question which was asked earlier. Do courses form a group? And also a question which nobody asked, but you should have seen, right? When we had this EABCDF group, the group S3, we had EA was a subgroup, so was EDF. And you form the left courses and right courses, you had 2 different scenarios. For EA, the left courses and right courses did not always match. For EDF, on the other hand, they always matched. Now, that brings us to a special kind of subgroup. A subgroup N of a group G is called a normal subgroup of G, and that has a special symbol, which is a triangle pointing towards N from G. If this happens, if you conjugate every element of the subgroup N, G and G inverse, of course, will be an element of the group G. But if you insist that G and G inverse this whole set, which means you take every element of the subgroup N, take every element of G and do G and G inverse with them. If the resulting thing is the same as the subgroup N, if the resulting set is the same as the set N, then you call the subgroup a normal subgroup. So a normal subgroup is simply also called an invariant subgroup because it's invariant under conjugacy. Remember, notice one thing, we are not really saying that the elements don't change. Gn1, G inverse might very well be not N1, but it will have to be another element of capital N. And if that works for every element of capital N, for all G, then you say that you have got a normal subgroup. And an important result, which is again something which is very easy to prove, homework. If N is a normal subgroup, this left courses and right courses must be identical, but that's sort of trivial. N is the same as G and G inverse, sort of immediately reads into NG equals Gn, right? Just by moving the G inverse from the right to the left. But you should really check that is really true. That if N is a normal, yeah, go ahead.
What about the converse of this statement? If left courses and right courses are identical?
And right courses are identical. If all left courses and right courses are identical, then N is a normal subgroup.
Oh.
Yeah, that's true. But that's important. It's all, right? Not any. Okay, that actually was a statement that I had. Converse is also true. Okay. Now, there are 2 normal subgroups which every group has by default. The trivial group, which is the group with only the identity, if you do G, E, G inverse, you're of course only going to get E. So you're going to get the group back. And the whole group is a subgroup by default. And if you take the whole group and do G and G inverse, you're of course going to get the group back, right? So these are always normal subgroups. Now you say a group is simple if these are the only normal subgroups. Okay. The trivial group and the whole group are always there as normal subgroups. If these are the only normal subgroups, you say a group is simple. And one important point, which I will not prove, but which again is very easy for you to prove, is that if you want to prove that a subgroup is normal, you don't really have to show that G and G inverse is equal to N. It's enough to show that for all G, G and G inverse is a subset of N. That is, every element of the form G small n G inverse is in capital N. If you prove that, then you can easily show that the subgroup is normal. That is, the inclusion also works the other way around. It's actually very easy to show, so I will not give you the proof of this. So now, let's come to this question about, can cosets form a group? Of course, for that you need to be able to multiply cosets together. And first, let's define how to multiply two subsets. So A and B are two subsets of group G. Now how do you multiply them? Simple, you know how to multiply group elements. How do you multiply sets? You just pick an element from the set A, pick another element from the set B, multiply them together, and do it for all the elements of set A and set B. And you get a collection. And that collection is a set, of course. And you just ask, just define that to be a product A. Okay. So the question now is, that was a question that now that we have a rule for multiplying sets, cosets are of course sets. The question is, can cosets form a subgroup? Cosets for a subgroup form a group under this multiplication. Okay. So you have a subgroup H of a group G. You have its various cosets. They're all of equal length, remember, the same length as H. Can they form a group under this multiplication? That's the question. So the answer in general is no. The reason for that is simple. This will violate closure. If you multiply two cosets by this rule, you will usually not end up with a coset. Just as an example, you take H as EA, our favorite subgroup for S3. Then two cosets AH is of course AE into AA, that's EA. And BH is BF, that's what we found out earlier. If you don't remember that, just take my word for it, that if you multiply this out, this is what you're going to get. And if you multiply AH by BH, that's of course EA times BF. So it looks like 4 elements because this is a typo, EB, EF, AB, AF. Right, it shouldn't be EE. E with B, E with F, A with B, A with F. And another typo, I missed the equal to sign, and I of course also missed the fact that this is really not EE, that should be AFDC. You multiply this out, the EA, EB is B, so this is BFDC, sorry, not AFDC, it's BFDC. Again, sorry for the typos, it was done rather in a hurry, so I messed up. This is the final result, not EFDC, but BFDC. That of course is not a coset. That's a different set altogether. So multiplying two cosets in general do not give you a coset. So typically multiplying the cosets under multiplication do not form a group of their own. But that's not the end of the story. The point is, if you have a normal subgroup, then multiplied G1n, so if n is a normal subgroup and you multiply the two cosets G1n and G2n, you are actually going to get a coset G1, G2n. Okay. That's a statement that I've not proven this. I'm just asserting this, that if you start with an arbitrary coset subgroup, take its cosets, multiply them together, you will usually not get a coset. However, if you multiply two cosets of a normal subgroup, the result is a coset. Well, the proof is sort of straightforward. The proof goes this way. Just look at the left-hand side, G1n, G2n. If any element belongs to G1n, G2n, that means it must be a product of an element of G1n, which is G1n1, and an element of G2n, which is G2n2. So there must be n1, n2 in the normal subgroup n, so that X is G1n1, G2n2. But now, let's just point out that you can make this, identify this with G1, G2, an element of G1, G2n by simply doing this. G2, G2 inverse is of course the identity, which you can put in anywhere you want, right? The identity can go in anywhere. But if you just put it in here, what happens? You get G1, G2 and G2 inverse N1, G2. So that's just associativity. Okay? That is, you can move the brackets wherever you want. So you can say, I will multiply G1, G2, I will multiply G2 inverse N1, G2, and then I will multiply N2. As long as you're not changing the order of elements, brackets you can change any way you want. But the important thing is, because capital N is a normal subgroup, G2 inverse N1 G2 has to be an element of capital N, right? That's a basic defining property of a normal subgroup. Take any element of a normal subgroup, find any one of its conjugates, it has to be in the normal subgroup. So G1, G2, this product has to be G1, G2, N1 prime, N2. And N1 prime, N2 is a product of two elements of a normal group. So it is in the normal subgroup. So X must be an element of G1, G2, N. So all we have shown here is that any element of this left-hand side is an element of the right-hand side. It's very easy to prove the converse. That is, this is one inclusion, G1, G2, G1N, G2N is a subset of G1, G2N, because every element here is an element of this. Proving the converse, that every element of G1, G2N is an element here, is actually absolutely trivial. I didn't even give a proof, I just said it's trivial. Of course, trivial means different things to different people, but in this case, it really means that you can do it without any work whatsoever. So you can actually show that these two are equal. Okay, at least one hurdle is crossed. If you have a normal subgroup, the product of two cosets is a coset. Okay, any questions so far? No. Yeah. Okay, let's move on to the next point. Now that we have a multiplication rule which is at least closed, that is, you multiply two cosets, you're getting a coset. Or do you have a group? The statement that I'm making is the set of all cosets, which is written G by N, by because it's called a quotient group, that's why the by notation, which is you take all the cosets together, and this works only when N is a normal subgroup. They form a group under the multiplication of sets. That's an assertion. The proof is simple. We have just now proven that G1 and G2N, if you multiply two such cosets, you do get a coset. So G by N is closed under this product. At least that was a big hurdle. We have crossed that. Well, why is it associative? Remember, this is a different product we are talking about. So we cannot really borrow the associativity of G directly. But it plays a role here. Remember, this is what associativity will have to be like. You have to check whether you can change the bracket from here and put it here. That is, you multiply the cosets G2N, G3N first and then multiply it from the left by G1N. It's the same as multiplying G1N, G2N and then multiplying it by right, from the right by G3N. Well, just use the rule that G2N, G3N is G2, G3N. And then use the rule again. It's G1, G2, G3N. But now this product is the product of the original group. This is associative. So this can be written as G1, G2, G3N. And that's the same as G1, G2N times G3N. So I'm now using the product rule in reverse. And G1N, G2N, G3N. So that's the associativity done for you. You're just using the associativity of the original group to prove that this is also associative. Well, you need an identity. So what would the identity be? If you look at the composition rule here, it should make it obvious what the identity should be. G1N should be such, if it's an identity, G1N should be such that when you multiply G1N by G2N, you should get back G2N. But you get G1, G2N, right? So what should G1 be? Obviously, it should be the identity. Or at least G1N should be the whatever you get when you put in En. That is, G1N should be N. And what about the inverse? G inverse, well, if G is an element of the group, G inverse is also an element of group. G inverse N is a coset. That has to be the inverse of Gn. Because G inverse N times Gn is going to be En. And En is N. That's the identity. Remember, the identity is the identity for this particular group. It's N now. So what we have is a new group which are formed when I have a group G and a normal subgroup. Using that, I can form a group called the quotient group, G by N. Okay. So this is the answer to the question: Can cosets form a group of their own? The answer is yes, if they are cosets of a normal subgroup, and then the group that you get from this is called the factor group or the quotient group. Okay, everybody clear? Because I'm now going to move on to the next topic. Okay, before I move on to the next topic, let me just give you an example of this. Perhaps that would be useful. Let's forget about this thing right now. Okay, so one rather non-trivial example of a normal subgroup. SLNR, remember, is a set of all n by n non-singular matrices with determinant 1. So all M which belong to SLNR have determinant 1. Okay, GLNR of course contains all matrices G such that G is not equal to 0. So SLNR of course is a subset of GLNR, and it's easy to show that it's a group in its own right under multiplication. So it's a subgroup. But is it a normal subgroup? For that, what we need to do is take every element M, any element M from this, take any element G from GLNR and form GM G inverse. And now ask, is this resulting thing in SLNR? So, question, is this determinant 1? The answer, of course, is
Yes, sir.
right? Because this is a similar transformation. Does not change determinant. So, GM G inverse belongs to SLNR. And this works for all elements in SLNR. So, what we really have is for all capital G belonging to GLNR, all non-singular matrices, G times the set SLNR times G inverse, which is just a shorthand way of saying 2GM G inverse for every M in this, is actually in SLNR. And as I said, this is all you have to prove, that this equal. At least because this is true for all G, you can easily show that because it's a subset, it's also equal. So you don't have to say subset, they're the same. So SLNR is a normal subgroup. So that's one. So homework for all of you. If it's a normal subgroup, you should be able to form a quotient group, right? So different cosets for SLNR, they will all have, there will be different elements of this quotient group. But if you work this out, you will find that this turns out to be a group which is very familiar and is something which you all know. This quotient group turns out to be something which is very familiar. It's one of the first examples that we wrote down actually. So I will just maybe worry about what this quotient group really is. Just let me give you a hint. If you take an element, any element G1 and form the quotient, from this quotient, where G1 is some group element of capital GLNR, some non-singular matrix. Of course, when you multiply them together, you do get this, right? That's a rule. But now what you have to realize is when you form all these cosets together, this coset says, look at this coset, G1 SLNR. Can anybody tell me what is, okay, this is a set, right? This is a set of matrices. Can you tell me what is common between all elements of the same set of this coset? There is of course a set of the form G1M where M belongs to SLNR, right? All of these are n by n matrices. All of these are non-singular n by n matrices, of course, but they all share one very important property. What is that?
The determinant is the same.
Exactly, they all have the same determinant. Okay. So basically, in fact, it works the other way around too. You can easily check that every matrix which has determinant 5 will belong to basically the same coset. Every matrix that has determinant 3.141 will belong to one coset, and so on. So basically there's a one-to-one correspondence, but there's only one real number which will not be featured here. Give me any real number R, you will be able to find a coset where every element has that determinant. There's only one real number which will not be featured here. Can you tell me which one that is?
0.
0, right. Because none of these matrices will have 0 determinant. So there is a one-to-one correspondence between this rather fancy looking thing. As a set, there's a one-to-one correspondence between this on one hand and set of all non-zero real numbers on the other. Not only that, when you multiply two cosets, this one is all the matrices which are the same determinant as G1. This is all matrices which are the same determinant as G2. The result is the set of all matrices which have the same determinant as G1, G2, which is determinant of G1 into determinant of G2. You should realize that if you take all the elements here with, say, which corresponds to the real number alpha, and the elements which correspond to the real number beta, that is all this entire coset whose determinant is beta, and you multiply them together, you get the coset of all such matrices which have determinant alpha beta. What that means is, if you look at this as a group, not as elements, but what kind of group properties they have, every element here is in one-to-one correspondence to a non-zero real number. And that correspondence survives the multiplication. When you multiply two elements, the element is also here. The resulting when you multiply the cosets and then find the determinant of the resulting matrices, the result is the same as if you had found the determinant first and multiplied them. Okay. So essentially these two groups they may have labels, which elements which look different, but as far as group structure is concerned, they're exactly the same. So these are called isomorphic groups. That's actually the topic that I'm going to talk about in general next. When are two groups to be considered the same group? So let's move on to the next topic, which is maps between groups. And this is very important. You have two different groups, G1, and now I'm being a bit more careful. So far I have used the standard abuse of notation that you replace the group, which is an ordered pair, remember, of the group element and the operation. Here I am saying G1 comma star 1 and G2 comma star 2. That is, I am also being careful to talk about the fact that the two operations may very well be different. One may be matrix multiplication, the other may be addition, or something entirely different. So you have two groups, G1 comma star 1 and G2 comma star 2, where star 1 and star 2 play an equally important role in defining the group, as do G1 and G2. The map F is of course a map between the sets G1 and G2. This is called a homomorphism if two properties hold. If it is onto and it obeys this very important property. You take two elements G and G prime of G1, compose them together, right? So of course for that you use a star 1 operation, that is the operation in the group G1. You get a result and then you apply F on that. If the result is the same as what you get if you applied F first on G and G prime separately to get F of G and F of G prime, which remember are elements of G2, right? And then you compose them using the rule for the second group, Fg star 2 Fg prime. And if this happens for all G and G prime, that is whether you compose first and then apply the map, or apply the map first and then compose, you get the same result in both cases, then you say that this map preserves group structure and is called a homomorphism. Homo of course means same. So it has the same structure. Morphism is essentially a statement about the structure. So homomorphism simply means G1 comma star 1 and G1 comma star 1 and G2 comma star 2 in a sense have the same or similar structure, to be more precise. Okay. So two groups are called homomorphic if there's a homomorphism between them. And by the way, I've added this one statement. We have added that a homomorphism has to be an onto map. That is, if you apply F on every element of G1, every element of G2 has to be in the image somewhere. Now this is a restriction which many authors put in. Some authors don't put in this restriction, but the reason why I put it in, again, this differs from book to book, but the reason why I put this in is because it simplifies many of the statements that will come later. So if I did not put it in here, then I would have to qualify most of those other statements by saying, if the map is a homomorphism which is also onto, then this works. To prevent that, I'm using the definition, I am putting onto right in the definition of homomorphism. Okay. The important point to note is that the two composition rules here may be very different. You're composing in two different groups. Okay. But this is, by the way, not something very unusual. You've already seen this lots of times before. Say, one of the most important things you have learned in linear algebra, for example, are linear maps. What are linear maps? You add vectors, then you map them. The resulting thing is the sum of the individual vectors mapped, right? That is, T acting on A plus B is TA plus TB. So basically, whether you do the map before the composition, before you do A plus B, or after you do the, or you compose after you do the map, you get the same result. That's basically what homomorphism is. So two groups are called homomorphic, and you write them with a tilde sign between them. Again, not really very uniform in notation. When you're reading a book, you should make sure what notation that particular book uses. If there is some homomorphism between them, you can find a map F with this property. It's called a homomorphism, and you say the two groups are homomorphic. Now, a homomorphism, which is also a bijection, that is, it's a one-to-one onto correspondence. That is called an isomorphism. Now, the name iso, of course, means identical here. So, and two groups which are isomorphic to each other are essentially the same group. As far as group structure is concerned, they are the same. So, basically, what this is saying is, f of g, if you do f of g, you are getting an element of g2. But that element of g2 is just a relabeling of that original element. As far as group structure is concerned, it's exactly the same. So isomorphic groups are identical as far as the group structure is concerned, and you write them with a tilde with an equal to sign below. This is just one version of the notation. Different books again use different notations. So this is a result I've been talking about lots of times. The group of symmetries of an equilateral triangle. This is a group whose elements are very different from permutations, right? Symmetries are reflections, rotations. Permutations are things you do to three objects. But as we have seen, and I'm pretty sure all of you should be convinced by now, that the group of symmetries of an equilateral triangle has exactly the same group structure as the group of permutation of three elements. And this is something we have been using so far. We have been calling that group S3. But basically, because I've been using this notion of isomorphism. Isomorphic groups, as far as group structure is concerned, are identical. A special kind of isomorphism is what is called an automorphism. It's a map from the group to itself, which actually keeps the group structure intact. So in this case, it's not a map between two different groups, but a map from G to G, which the property that f of G1, G2 is Fg1, Fg2. Now this is, okay, this is again something which we will use later. These are all basic group theory, but I have to sort of go through all of this because we are going to use these later. If you collect all the automorphisms together, the automorphisms are maps acting on a group G. But you can compose automorphisms, right? Or you can compose maps. You know how to do that, right? We have been doing that all the time. You just apply one map after the other. So you start with a group G, which may be a group of some elements. You have a map on the group G. And if you have more than one map on the group G, you can compose them together. And then you can ask, do the maps form a group under this composition rule? And it's very easy to show that you would take all automorphisms of a group G and compose them together. The resulting thing forms, the resulting set is a group. And this group is called Aut G, the set of all automorphisms of the group G. Now, there's a very special class of automorphism which we are going to use, we have already used. These are called inner automorphisms. They arise from conjugacy in the sense that you define a map Ig. For every small g, you define Ig. What is that? Ig is a map from G to G, which takes an element of the group, let's say G prime, to G, G prime, G inverse. So basically, takes in G prime, returns its conjugate after application through conjugation through small g. So this is the one which I used to write down the table earlier. Okay. And you can easily show that the set of all isomorphisms of all inner automorphisms, on the group G is actually a normal subgroup of odd G. This is a slightly non-trivial thing, but I'm pretty sure if you just sat down and worked on it, you should be able to work it out. If you can't work it out, you can ask me later. I will explain how this works. So I will just show you one thing. That is, I need to show you this at least, that this really is an automorphism. So Ig acting on G prime gives you G, G prime. Sorry, let me just erase the cutter here. So what is Ig when it acts on G1, G2? Is G now this is something which should be very familiar to all of you from what you have done with matrices and similarity transformation matrices. You must have done this before. But you can do it whenever you have associativity and inverses, right? You don't have to don't need matrices for this. But what is this? This is Ig G1. And this is Ig G2. So Ig acting on G1, G2 is Ig acting on G1 times Ig acting on G2. So Ig is a homomorphism, but it's also an isomorphism. How do you show that? It has to be one-to-one and onto. Onto part I will leave you to worry about. How do you show it's one-to-one? Simple. If G1, G inverse is G2, G inverse, then it's easy to see by applying G inverse from the left and G from the right that this immediately leads to G1 equals G2. So it's one-to-one. It's equally easy to show that it's onto. Just for want of time, I'm not showing the whole thing, but this shows that Ig is an isomorphism. Okay. And on the other hand, what is Ig1 times Ig2? Remember, these are maps, right? Because these are maps which act on G to give you an element of G. The best way to answer what this product is to see what they do to an arbitrary element G of group. So take any element small g of capital G. What does Ig1, Ig2 do? It's Ig1 and Ig2G. What's Ig2G? That's G2, G, G2 inverse. Ig1 acting on that, right? But what is Ig1 acting on? So this is a group element on which Ig1 acts, but what does Ig1 do to that? It just takes, again, something which should be very familiar to all of you from your study of matrices. G2 inverse, G1 inverse, which is, this thing is of course the same as G1, G2's inverse. So for any group element G, Ig1, Ig2 acting on G is the same as Ig1, G2 acting on G. So you have this rule. Using this and using a bit of manipulation, it's very easy to show that the group of all inner automorphisms is actually a normal subgroup of the group, a normal subgroup of odd G. Okay, this is not very important. And there are some theorems which are very important. Again, theorems which are very easy to prove. I will not give you the proofs, but theorems are important to know on their own. The kernel of a homomorphism, this is an important definition. Given a homomorphism F from G1 to G2, the kernel is defined to be the set of all elements of G1 which map onto E2, the identity of G2. Of course, there's one element which always does that. You can easily show from the definition of the homomorphism that F of E1 is always E2. So kernel of F is always non-empty. At least E1 is there. But more than E1, other elements than E1 could also be in a kernel. Remember, a homomorphism does not have to be one-to-one. So it's possible that there are more elements which will map onto E2. Now, the theorems that are important is, one, this is not really one of those isomorphism theorems, but it's a very standard result to prove that Kerf is a normal subgroup of G1. Okay, let me just show you the proof of this, because the proof illustrates the kind of techniques that we need to use. So F is a map from G1 to G2. You need to prove that the kernel of F is a normal subgroup of G1. Now, for this, what you need to do is take an element K from the kernel, take any element G from the group G1. So G belongs to G1, K belongs to the kernel of F, and ask, is this element in the kernel? And how do you check? You just apply this. But this is Fg, Fk, Fg inverse. Why? Because that's what a homomorphism does. You can apply the homomorphism before and then compose, or compose first and then apply the homomorphism. But then it's easy to show. Now, what is Fk? Fk is E2, right? Because Fk is E2, it's simply Fg, F of Fg inverse. That's obviously F of Gg inverse, which is F of E1. We always show that that's E2, which means Gk G inverse also belongs to the kernel. Or this immediately shows that the kernel of F, a subset of the kernel of F, and that's all you really need to prove that this is true. So that's the kind of argument we use here. Okay, so going back to the isomorphism theorems. Well, first isomorphism theorem, very, very simple. It says that if the kernel of F is only E1 and nothing else, remember E1 has to be in the kernel. But if that's the only element in the kernel, there's a sure shot way of showing that a homomorphism is an isomorphism. A homomorphism is an isomorphism if and only if the kernel of F is a trivial kernel, just the identity and nothing else. Okay? On the other hand, if the kernel of F is not just the identity, it's a non-trivial subgroup, even then it's a normal subgroup. We have just learned about quotient groups. So we can form the quotient group G1 by kernel of F. And the isomorphism theorem tells us that this is identical to G2. This is a result which is quite useful. We will use it several times during this workshop also. The proof is actually rather simple, but I'm not going to go into the proof simply for want of time. And a very important corollary of this is this. Well, we will need it later, so we will come back to this later. Zg is a special subgroup of any group. Is called the center of the group. Is the set of all elements in the group which commute with every element of G. So Zg of course is non-empty because E, the identity of course belongs to Zg. And if the group is abelian, then the entire group is Zg. But if the group is non-abelian, even then there will be multiple elements which all commute with every element in the group. And they will all form a normal subgroup of the group G called the center. That the center is a normal subgroup, again, is very, very easy to show, but these are things which I'm just skipping over. And a very important corollary of this result is of this isomorphism theorem, the second isomorphism theorem, is that the normal group, when you form the quotient group G by ZG, you get something which is isomorphic to the set of all inner automorphisms caused by the group G. This is a result which will be very useful, but I'm skipping the proof for the time being. We are going to come back to when we use it, and you will see that. Yeah, any questions?
Sir, what is ZG? Can you please?
ZG, as I said, is a center. It's called the center of a group G. Is by definition the set of all elements of a group which commute with every element of the group.
Okay.
So if you took E, A, B, C, D, F, our example, the center was just E alone, because nothing else commutes with every element. But if you took the example of the element of the symmetry group of a square, then the center will be E and G. E and G individually commute with every element. So that's the center.
Okay.
And the center is a normal subgroup. That's easy. That's very easy to show. It's slightly non-trivial to show that G by ZG is identical to isomorphism, this inner automorphism group IG. Okay, the final part for today. This actually, so I am really going at half pace because this is what I wanted to finish in the first lecture. Direct and semi-direct products. This is how you build up big groups out of small groups. Okay. And this is also where this notion of simple, semi-simple, etc. will come in, semi-simple groups and so on. Because you will essentially see that a big group which is not simple can be broken up into small pieces which are all simple. Simple, remember, are groups which don't have non-trivial normal subgroups. So if you can break up a group into its normal subgroups, you can sometimes see that you can build up a big group out of small groups. And properties of very large groups can be understood in terms of rather smaller groups, which of course is always a good thing. Understanding small things are easier than understanding big things. And this idea, essentially, this idea of building up bigger groups from smaller ones, this is actually going to be very, very handy when we talk about various things, including the representations of groups that we are going to talk about in the next lecture. So given two groups G1 and G2, the direct product group is very simple. The direct product group is written with G1 outer product symbol with this O cross symbol here. But as a set is the same as the product. I hope everybody knows what the Cartesian product of two sets is. The Cartesian product of two sets is simply you take pairs of elements, one from each group. So this is it. You just take a pairs of elements. That's one element of G1 direct product G2. G1 comma G2, where G1 comes from capital G1, G2 comes from capital G2. Okay. But of course, this just defines the underlying set. How do you define the product? The product is defined very, very simply. You take the element, the element G1 comma G2 and the element G1 prime comma G2 prime. You want to define how to multiply this with this. The answer is, well, G1 and G1 prime are both elements of the first group G1, G2 and G2 prime are elements of the second group G2, and they just compose independently of each other. G1 just composes with G1 prime according to the rule of the first group, and G2 just composes with G2 prime according to the rule of the second group. Nothing really great, nothing new, right? All you are saying is the two groups essentially work on their own. Okay. But there are many situations where large complicated groups can be broken down this way, that you essentially have two groups which work entirely on their own. Okay. So the smaller groups essentially are doing their own thing, and that's what is giving rise to this big group structure. So by the way, if say one of the groups has 4 elements, G1 had 4 elements, and G2 had say 10 elements, G1, G2 will have 40 elements, right? Because the first element has first element of this pair has 4 choices, the second one has 10 choices. There are 40 possible elements. So you get 40 element group built out of 2 much smaller groups. And that's just the beginning. You can of course take the direct product of G1 with itself, with itself, with itself, and so on, and keep on getting bigger and bigger groups. And essentially, in each of these bigger groups, each group element, each smaller group essentially does its own thing. So direct products are really very, very simple. Now, well, there are two subgroups of a direct product group which are very, very easy. One is hold G2 fixed at E2. So take G2 to be identity of the second group always, and let G1 run over the entire group G1. And the other one is let G1 be E1, let it be fixed, and just let G2 run over the entire group G2. These two subgroups, these are easy. It's easy to see from the basic rule that these are going to be subgroups of the direct product group. And these are, of course, isomorphic to G1 and G2, because if you look at this, there's an obvious one-to-one correspondence between pairs of this kind, G1, E2, and the elements G1 of capital G1. Just pick out the first element. That's the isomorphism. It's a one-to-one correspondence, and it's easy to see from this multiplication rule that it actually allows you to keep the group multiplication rule intact. That is, if you take G1, E2 and say G1 prime, E2, what is the product going to be? It's going to be G1 prime into E2, E2. And E2 here is going to be identity. So again E2. So it's going to be G1 prime, G1, E2 times G2, G1 prime, E2 will be G1 prime, E2. So basically the rule is the same as the multiplication rule in group G1. Similarly for this, the rule is the same as the multiplication rule for the group G2. So these are essentially, it is obvious that these are subgroups of G1 cross G2. Not so obvious, but not very difficult to prove that they are actually normal subgroups of G1 cross G2. Let me just show you one example, one of them. So take an element from, this is not G1, but let's call it G1 bar, which is isomorphic to G1. And we are taking one element from that, which is G1, E2. Take any element from G1 cross G2. Remember, when you prove that something is a normal subgroup, you take every element from the parent group and try to form. So you take any element G bar, where G and G bar, G belongs to capital G1, G bar belongs to capital G2. And take its inverse. Now, I did not prove this, but it should be very easy for you to work out. The inverse, simply because the groups essentially work on their own, the inverse of G bar is simply G inverse, G bar inverse. Each one gets inverted on its own. Because when you multiply this and this, you're going to get G inverse identity. Of course, identity of the first group, G bar inverse identity of the second group. Put them together, what do you get? If you just use the group multiplication rule, where essentially the first group multiplies on its own, the second group multiplies on its own, get G inverse, G bar inverse. That's for the first element. For the second, sorry, not G bar inverse. Sorry, I wrote it completely wrong. So let me just. What you're going to get is G1, all the first elements are going to get multiplied, G inverse. The second elements are also going to be multiplied, G bar, E2, G bar inverse. What is this going to be? Remember, this is an element of capital G1, remember? The small g, because small g belongs to capital G1, small g1 also belongs to capital G1. An element of capital G1. What is this? This is E2, right? Because this is the identity, so this will just commute. And you get G bar inverse, and you get just the identity. So notice that this G1, take any element from G1 bar, hit it with any element small g. This small g actually stands for this pair here of G1 cross G2. And G inverse on the right, you actually get an element of G bar again, G1 bar again. So G1 bar essentially is a normal subgroup. And since G1 is isomorphic to this, basically we say G1 is a normal subgroup of G1 cross G2, so is G2 a normal subgroup of G1 cross G2. And it's very easy to show, and this is where the notation really comes to life. If you take of course, if you have normal subgroups, you have quotient groups, and G1 cross G2 quotiented with G1 is isomorphic to G2, and G1 cross G2 quotiented with G2 is isomorphic to G1. So this is where the notation. Okay, again, a result which I'm not proving, a result which I'm pretty sure you will be able to prove without much difficulty. But this result is basically what shows that you can break up a big group into smaller pieces this way, or take smaller groups and build them together to form a bigger group. Now there are some conditions under which this can happen, but let me just, I did say that I will not talk much about physics, but I should talk something about physics. So when do direct product groups occur in physics? Well, if you have a composite system, different parts may be symmetric under different groups. And the overall system will be symmetric under the direct product of this group. So basically a system may have two different pieces. A particular symmetry operation, set of symmetry operations act on the first one. A particular set of symmetry operations act on the second one. Now if you say, I treat them together as the same system, but when I do symmetry operations, I apply the first set on the first part, second set on the second part, so they never mix. Then what I have for the symmetry set for the whole group, for the whole system, is a direct product of the original groups. And one such direct product is actually very, very famous. I'm pretty sure all students of physics have heard of it, if not already studied it. That's the SU3 cross SU2 cross U1 symmetry of the standard model of elementary particle physics, which is the closest we have to theory of everything. Basically, here you have three different subsectors of particles which transform under, one set transforms under SU3, another transforms under SU2, the other transforms under U1. What these mean, well, hopefully they should be clear by the time I end my lecture course, if you don't know already. But the important thing is, these are independent symmetries acting on different parts of the whole system, and the symmetry of the standard model as a whole is a direct product of these symmetries. So direct products are actually pretty important and interesting. It's also very interesting to know when can you write a group as a direct product of its subgroups. And the theorem is this. Theorem is that if you have two normal subgroups N1 and N2, which are both normal subgroups of G, now N1 and N2 cannot be disjoint because N1 and N2 are subgroups, so they must have the identity in them. But if their intersection is just the identity and nothing else, and the group G is the product of the two sets. Remember, when you say product of the two sets, you mean every group element can be found by multiplying an element of N1 with an element of N2. Then G is isomorphic to N1 direct product with N2. So when is a group a direct product of its normal subgroups? If you can find two normal subgroups with this property, then the group G is a direct product of its normal subgroups. The proof is here, but I'm skipping the proof just for want of time. I will come back to the proof later if I have time. But for the timing, let's just skip the proof and come to something else. We have talked about the direct product, and we have seen that the direct product is very, very straightforward. It's just each part of a system transforming on its own. Now let's talk about how situations where you need to go beyond the direct product. And there happen to be very important situations where the direct product is not enough. And I'm pretty sure somebody or the other will talk to you about perhaps even this particular group, the Poincaré group. Well, in a real class, I would have asked for a show of hands as to how many of you already know about the Poincaré group. But if you don't, let me just point out that all of you should know this, that all theories of physics are symmetric under Lorentz transformations, right? That is, x mu goes to, so x0, x1, x2, x3, four coordinates. x0, of course, is CT. Goes to new space-time coordinates given by a matrix lambda mu nu. So lambda mu nu acting on the original column vector. And this really just says where eta mu nu is +1, -1, -1, -1 along the diagonal. This really just says that this is a transformation under which x0 square minus x1 square minus x2 square minus x3 square is going to be invariant. So these are called Lorentz transformations. These are obvious symmetries. So if you don't even know much about Lorentz transformations, just think of them as some matrix lambda acting on a column vector x. That's all that you need right now. Well, there are other symmetries which are obvious symmetries of all physical systems, all laws of physics at least, which is translations. You just translate space-time coordinates. That just means that you're changing your origin. Okay, so your coordinates have different values. They have been shifted by constant. X0 has been changed, time 0 has been changed, space, x component, y component, z component has been changed. So when you combine these two transformations, you get what is called a Poincare transformation. It's denoted by lambda comma a, and what it does is changes x mu to a new vector x prime mu, 4 vector x prime mu, which is lambda mu nu x mu plus a mu. So basically a matrix lambda acting on the 4 by 1 column vector x plus a 4 by 1 column constant column vector added to it. Any questions so far? Okay. So this is a shortened notation which is easier to deal with. Yeah, any question?
Sir, there's a bit unclarity that how come that product is being distributed only to the first product, not the whole one. In short, where you mean
which one? I didn't understand that. Which question which one are you asking about?
See the equation in the red color, sir, where you are showing the Poincare transformations.
Yeah.
Symmetrical. So one property has been used. That is very clear. Both the above properties are being used: Lorentz transformation and translations. But but in the right hand side, we don't see the things are being fully. Maybe I'm confused, but I want to make it clear.
No. What I'm saying is a Poincare transformation is basically what it means. You first do a Lorentz transformation, then do a translation. Does a Poincare transformation lambda comma a?
Okay.
Of course, you could have done it in the other order. You could have first done a translation, then done a Lorentz transformation. That would have ended up giving a different Poincare transformation.
Okay, sir. I got it.
Okay.
Okay.
Our notation lambda a stands for this one. That is x prime goes to lambda x plus a. But actually what you have pointed out right now is going to be very important. The importance comes in when we try to talk about two Poincare transformations, one after the other. You all know the set of all Lorentz transformations. Okay, maybe you all already know it, or if you don't, you can easily verify this. The set of all Lorentz transformations do form a group called the Lorentz group. And the set of all translations, which is just add up a constant 4 vector to every one of the 4 vectors, they also form a group. These are very simple groups on their own. Of course, the Lorentz group is not that simple, but the translation group is really very, very simple. The set P, which essentially contains a Lorentz transformation and a translation, just like a direct product contains an element G1 and an element G2 from capital G1 and capital G2 respectively, is a product of the two, but you notice that the product is being written with quotes. Why the quotes? The answer is, how do you combine Poincare transformations? And the answer is, you start with an x and then do one transformation, say lambda 1 a1 first. What happens? X becomes x prime, which is lambda 1 x plus a1. Okay, remember, there is a definition of lambda 1 a1. You first apply lambda 1 and then translate by a1. So this is a new x prime. Now you want to do a second Poincare transformation, lambda 2 a2. So what happens? Well, lambda 2 a2 acts on x prime. So lambda 2 x prime plus a2. As simple as that. So now let's figure out what is this when you think of that as a single transformation acting on x, the original 4 vector. So what is x double prime? X double prime is lambda 2 x prime plus a2, but x prime is lambda 1 x plus a1, right? So now it's simple and trivial algebra. Just open it out and you get this. Lambda 2 lambda 1 x plus this. Notice, okay, this is easy to see. This is a product of two Lorentz transformations. It's actually a Lorentz transformation. Okay. This, on the other hand, is a constant vector which you add afterwards. That's the translation. So the combination rule is lambda 2 comma a2 is lambda 1 comma a1 is lambda 2 lambda 1 comma lambda 2 A1 plus A2. So notice that here something rather strange is happening. You have the translation group. Translations, of course, when you do one translation A1 followed by translation A2, you get A1 plus A2 as a translation. If you do lambda 1 first, then you do lambda 2, you get lambda 2, lambda 1 as a Lorentz transformation. Both of them are groups on their own right with their own product law. But when you are putting them together in the Poincare group, the composition rule is not just not that each group does its own thing. Notice lambda 2, lambda 1, Lorentz transformations, they combine on their own. No worries about the translation. The translations don't combine on their own. The result is not A1 plus A2. The result is lambda 2 acting on A1 plus A2. So this is not the direct product. It's something different. It's called a semi-direct product, where the one part composes on its own, but on the other part's composition, the first part plays a role. Okay. I have the formal definition right after this, but I'm not very sure that the formal definition will be that useful. The Poincare group is one very important case where you use this. Okay. Now, I'm not very sure what all of your backgrounds are, but if you have done at least BSc physics, which many of you must have done, you should be able to at least cite one other example. Definitely, if you have done first year MSc physics, you should be able to cite one other example of this semi-direct product structure which you have already seen. Two distinct groups combining together to form a bigger group, but the bigger group is not such that each group just works on its own. Can anybody give me? Can anybody guess an example? I'm assuming that there are plenty of students here who have studied first year, say, MSc, right? Have you heard of a group? In fact, have you even heard the term group used anywhere beyond the mathematical physics course? If so, where? Anybody?
Sir, I think it will be in Galilean group, I think.
Galilean group. Okay, Galilean group is the group of rotations and translations.
So,
right.
I mean that
But that's essentially
essentially
the 3D version of the 3D version of this, right? 3D version of the Lorentz group, translation group thing. It's essentially the same thing in 3D. Okay? That's the Galilean group. But I was not aiming at that. I was aiming at something else from another branch, a different branch of physics, where you also see the same nomenclature used. Any other group you have heard of in any other branch of physics, apart from mathematical physics and high energy physics, for those of you who have done high energy physics?
So rotational
I've
group.
all done rotational group, of course, you have heard of, but again, that's sort of the same thing here. Okay, but the one I was talking about is also. Okay, this is a situation where, of course, the question I'm asking can only be answered if you know my mind, right? Because I'm aiming at a particular answer which you may not be thinking about right now. But let me just give you a hint. Solid state physics. What groups have you heard of there? You must have heard the name.
Sir, crystallographic point groups.
Good. Point groups and?
Answer, I don't remember anything else.
Okay, but the moment you hear about point groups, there's something which comes after that. Something which we find.
Point group.
Dihedral group.
Okay. Wait. Let me just give you the answer. Point groups are essentially group operations which leave one point in a crystal fixed. Okay, but there's another symmetry which every crystal has. What is that?
Space translations.
Spatial translation. Not all space translation, but very special space translations, right? Space translations by the lattice vectors. Right? So you have a translation group, not the whole full translation group as you have here, but a subgroup of the translation group. And you also have a point group.
About certain fixed length. Translations about certain fixed length.
No, not for certain fixed lengths. Translation about, okay, not certain fixed length, but many fixed lengths. There are infinitely many elements, right? Every lattice translation.
Yeah.
That would be a symmetry. Every lattice translation would be a symmetry, right? Is that okay? If you remember your solid state physics a bit, you have a crystal lattice, and any vector which joins two crystal lattice points, that defines the translation, and translation through that amount will be a symmetry of the entire crystal. Yeah, of course, assuming that the crystal is infinitely big and no edges and so on. But these are two obvious symmetries. One could be symmetries which leave one point fixed, could be some rotation, some reflections, and so on. That's the crystallographic point group. You also have translation groups, and you put them together, you get what is called a space group. You must have heard of the space group, right?
Yes, sir.
Yes, sir.
And the space group essentially is a point group operation followed by a translation, and by exactly the same argument that we gave right now, you would notice that that's a sorry, there's a call coming in. Let me just take that. Hello. Hello. Okay, I've missed the call. Anyway, doesn't matter. Okay, the space group also is a semi-direct product of the crystallographic point group and translation group. So semi-direct products are actually very common. They are also very useful. The point is, if you know how to talk about smaller groups, you can use them to talk about bigger groups. So in fact, there will be definitely one lecture in this series on the Poincaré groups representations. I'm not going to talk about that, but the all important thing there will be the Poincaré group is a semi-direct product, and that semi-direct product structure will be exploited in that. Okay, so I've come to the end of whatever I wanted to talk about in the first lecture. So that has taken me 2 lectures. I will definitely have to speed up for the next part. But the next part is really, the next lecture will essentially be on representations, which is where you actually use groups in physics, or how you use groups in physics. So that will be tomorrow. Okay? I will just wrap up today. If there are no questions. If there are questions, I can always answer them. So if not, yeah.
So just I wanted to ask, tomorrow you have 2 classes which are decoupled. I mean, the first class, then there is another class in between, and then you have the third class.
Yeah.
So you want them together? You want them?
No, decoupled is fine. I have no problem. Unless the students forget in the middle, or maybe the students will also need some respite from hearing the same thing.
Actually, Professor Sachin was asking that, like, in case you need them combined, then it's fine with him. So I just wanted to ask.
If he wants to, if he has some reason to move back, then it's fine. Otherwise, it's okay with me.
No, he doesn't have to, just he wanted me to ask you whether you are comfortable that way. He doesn't have a problem with any of
Okay, anyway, I think a gap will be okay, because it might give the students some respite from me. They've heard me long enough, I guess.
No, it's all right.
And they will hear me for very long.
Yeah, I would like to request participants that every morning you please check your mail. If there is any sudden change in schedule, I will be informing you over mail. So please check your mail. Yeah, so I was just interfering in this whole business. So can we please like go back and?
No, I'm done. So if anybody has a question, I can of course answer now.
Yeah, sure.
Or if anybody wants to see some details of a calculation or whatever.
Available. Excuse me, sir.
Yeah.
So can you make the slides available? Is it possible?
It is possible, but the only problem is the slides are huge. And one thing, I can make it available. The one thing which I will definitely ask you not to do is print them out. Because if you print them out, you're going to waste resources like anything.
Okay.
Because all these pictures that you saw were essentially different pages.
Yeah, just I wanted to tell that we are going to upload in the YouTube. We have a YouTube channel of the department. We are going to upload them, the lectures.
No, they're asking for the slides, I guess.
The slides, that is why they need particularly the slides I am asking. If they do not need the slides, they can have the lectures.
No, I have no problem sharing the slides with them. I can give the slides to you and you can share in your sites or whatever.
Sure, I can. If it is required, I can do it.
But I will need some time to make to correct a few typos which I've noticed, because I don't want the slide to go out with mistakes. That's going to be harder.
That's very true.
So just wait. I will share the slides.
Okay.
But please don't print them, because these are 1,000-page or 2,000-page slides. Complete waste of paper. These are meant to be seen on a screen, not printed.
Okay. Okay. Also, sir, would you like to refer something, any book for elementary group theory?
Elementary group. Well, look. There are two entirely different topics. One is group theory seen from the point of view of a mathematician. Another is a group theory seen from the point of view of a physicist. And what we are doing is, what I said today was essentially mathematical group theory, not the physicist part. I will start with the physics part tomorrow. That is the part which the physicist really uses. But there are many different books, most of which use different notations, and that becomes a bit confusing if you are following too many of them. You want one book, difficult to say one book which is good for all of this. But there is a recent book by somebody called Wolfram, not the same Wolfram as the one who wrote Mathematica, but another Wolfram. And, well, a second author whose name I simply cannot pronounce. Glue or something. If you search with Wolfram and group theory, is group theory in atoms, solids and molecules and something like that. It's a decent book. You can try referring to that. There are many very good books, of course. There's a book by Sternberg, which is very good. There are books by Eliot and Dauber, classics, Hammermesh, and so on. But no one book will have everything. But this Eliot Dauber is good. There's a very delightful book which you can read by Z. It's called Group Theory in a Nutshell. The only problem with that book is that book actually has many mistakes. Well, I shouldn't really call it a mistake. I should really say that there are many statements made in the book which are correct for that particular context, but which are wrong in general, and Z does not really very carefully distinguishes the case. So there are many statements which Z makes, it seems very simple and which actually works in the context in which he is making them, but which are wrong in general. So you have to read those books. That book is a very nice book to read. It's wonderfully written. It has very nice stories and backstories and pictures. But, well, you may end up with the wrong idea about some of the mathematics if you just read that and nothing else. But one book I would say Wolfram is a good enough.
Okay.
Excuse me, sir.
Yeah.
Hello. Sir, I have some doubts about the conjugacy classes you taught, and what is the difference between, like, if I have an element G1 is conjugate to another element G2, and the definition that, I mean, two elements being conjugate to one another and the conjugacy class, what is the relation?
Okay.
I mean,
I guess I think that has to be clarified. Two elements, suppose element G2 is conjugate to G1. Let's write it like this. I'm just borrowing the symbol for the time being. This happens if there exists a group element G somewhere in the group such that G2 is G, G1, G inverse.
Yes, sir.
Okay, if this happens, then G2 is conjugate to G1. The conjugacy class of G1 simply is all elements G2 such that there exists a G in G such that G2 is G, G1, G inverse. So conjugacy class is simply all the elements which are conjugate to G1. Take them all together.
Okay, sir. Okay, sir. Thank you, sir.
That's what a conjugacy class is. Okay.
Yes.
And
Sir?
of course, did I write G? Okay, yeah, go ahead. Any other questions?
Sir, I have a doubt in the equivalence classes.
Yeah.
We know that two equivalence classes are disjoint, and the union of all the equivalence classes gives the whole group, right?
Yeah. Whole set. That's a equivalence classes are notion from set theory. They
whole
exist
set,
even beyond. So, yeah, right.
So I have been studying other day these Hausdorff spaces. So is there any relation between them, since two open sets which are disjoint and the union of the open sets gives the
Well, that really is beyond this scope of this discussion. Hausdorff spaces are basically a topological concept, right? You have two open sets which are disjoint, one containing each one of the points.
Yes.
That's a different structure altogether. So it's better not to connect that with this one.
Okay.
No, this is not the same thing.
Okay, sir.
Sir, I had a question. If you could go back to where you were defining semi-direct groups.
Yeah.
Are there any specific constraints that we require on the two groups that we are using to define the semi-direct product? Because
actually there is, because if you just looked at my example, we had the Lorentz group and the translation group, right? But the way we combined the elements, lambda 1, A1, lambda 2, A2, gave you this lambda 1, lambda 2. This was just the Lorentz group acting on its own, so no constraints coming from there. But then you had lambda 1, A2 plus A1 as a translation. It came out simply from the algebra, but what you have to realize is that lambda 1 is why is this at all legitimate? This construction? Because A1 ultimately are 4 vectors, is a 4 vector, A2 is also a 4 vector, and lambda 1 is a 4x4 matrix which can act on a 4 vector, which is essentially a 4x1 column vector, right? So it's truly possible for the elements of the group L to act on the elements of the group T. In other words, without that, you cannot have semi-direct products. Okay, maybe I should really show you the formal proof, formal definition, because that actually clarifies this. So a semi-direct product cannot be formed between any two groups. It has to be a group G, another group which is curly G, which is actually automorphic to a subgroup of, isomorphic to a subgroup of odd G. In other words, elements of curly G can either directly, it can be elements of odd G, say, could be odd G itself or odd G subgroup, which means elements of curly G should be able to act on the elements of capital G. Okay. Either they can act on them directly or they can be isomorphic to something which act on them. And then the semi-direct product can be defined. In which what you see is basically you take the element small g from capital G and alpha from curly G. And when you're combining them together, notice alpha gets to act on G prime and only then does it combine with G. Okay. Now, because alpha gets to act on G prime, alpha must be such that it will act on G prime. So, act on an element of capital G. So, you cannot have any two groups. The second group must be a isomorphic to a subgroup of odd G. Okay, that's the formal definition. In our example of Lorentz and translation, can you tell me which one is which one of capital G and curly G? Which is which?
Yes, sir. So curly G there will be the Lorentz group will be isomorphic to a subgroup of automorphisms of the 4 vector space. So,
yeah, so capital G is translations actually.
Yeah, capital G will be translation.
And curly G will be the Lorentz group because it's isomorphic to operations which act on some subset of operations which act on capital G. Okay, and the general theorem that you have a theorem very similar to the theorem for direct products. You start with two subgroups N and H, and G is N times H. So N has to be normal, H may not be normal. So remember when we were talking about direct products, N1, N2 both had to be normal subgroups of G. Here N is a normal subgroup of G, H is a subgroup of G with this special result that the center of the subgroup H is just the identity. So it is a trivial center. There is no non-trivial element of H which commutes with every other element of H. If that happens and N and H are nearly disjoint or as disjoint as they can be, remember they are both subgroups, they must have E in common, and G is the product, then G is isomorphic to the normals, this semi-direct product. Okay. So this is the theorem. I skip the theorem. The details of the theorem are not that important for us, at least not until we go much deeper into the theory. But basically, here also you see this H looks like any subgroup, but what is really appearing here is not H. It's actually the inner automorphisms induced by H, which of course can act on every group element, including the normal group elements. So you need two groups, one of which can act on the other. Otherwise, semi-direct product makes no sense. Okay, so semi-direct products are of course more complicated than direct products, but they have many of the simpler features of direct products as well. So, which is why they're interesting. Okay.
Sir, can I ask you something?
Yeah, go ahead.
For tomorrow, sir, as you will be discussing characters and mostly molecular vibration.
No, I will not really be discussing molecular vibrations really. Okay, let me clarify. I will not be talking about molecular vibrations per se. I will be talking about representation theory and characters, and molecular vibrations will just play a small role there as a sort of application. I may not even get to mention molecular vibrations, but I would try to. Okay. So if your question was, will you have to read up molecular vibrations first? I'm pretty sure if you remember your small oscillations, the basic theory of small oscillations that you learned in the first year or so, that should be enough.
Okay. Thank you.
Of course, you can read up the entire group theoretical theory of molecular vibrations. That's a different ballgame altogether. I'll just try to indicate where group theory is used in molecular vibrations. I will not really talk about molecular vibrations as such. Because my mandate is to essentially teach you the basics of the theory so that you can use it elsewhere. And the other speakers will also give you plenty of physics applications. So I'm not really going to talk too much about physics applications. Any other question? So there's a question in the chat. What is the name of the YouTube channel? I, of course, cannot answer that, but I'm pretty sure the organizers can.
I'm there to answer. So I wrote it for people didn't notice. This is Department of Physics, Assam University, Silchar.
Okay. So it will be somewhere in the chat also, right?
Sorry?
You wrote it in the chat somewhere? Yeah, you did.
Yeah, I wrote somewhere, but I don't know. I don't remember exactly when. But yeah, that is the Department of Physics, Assam University, Silchar. You can really subscribe that channel so that for the time being, at least you can unsubscribe later. But you can just keep it subscribed for the time being so that you know whenever I'm uploading whatever.
Yeah, that will be a good idea. And the next session is at 7:30 or is it?
7:30.
Okay. And again, so there's enough time for me. I have time. So if people want to ask questions, go ahead.
So one leisure question, though this is not very relevant, even then I'd like to ask you, why we differentiate between, that is more artistic question, Lie algebra and group theory, they are together only, same only, but is there any difference normally?
Well, I will talk about Lie algebras hopefully. Hopefully I will be able to talk about Lie algebras at the pace I'm going. I'm a bit scared whether I will be able to talk meaningfully about that. The basic idea, look, algebra is really different from a group. An algebra is a vector space on which a product is defined. Okay. So you realize what a vector space is, right? You can add or subtract elements there. Right? So when a Lie algebra comes in, you can actually add, in addition to multiplying elements, you can also add or subtract. Okay. So that's a different structure. Now, why is there a connection? The important thing really is that if you think of Lie groups, Now, Lie groups, of course, we are going to talk about later, but let me just talk about one simple example of Lie groups which everybody knows, the rotation group. It's a group of which is continuous, right? Because you have kind of a very small rotation, you can have bigger rotations, you can have slightly bigger rotations, and so on. And basically, you can build up a big rotation by rotating by tiny amounts, starting from no rotation at all. Okay? Yeah?
Yes,
sir. Start from no rotation at all, and you can slowly build up to the whole thing. And you can show, and I hope to be able to show that in this set of lectures, is that if you want to know what the rotation group or any Lie group, any group like this does, even when the elements are big meaning far away from the identity, the structure essentially is dictated by what's happening very close to the identity. So if you know the identity and its immediate neighborhood, you know everything that you need to know about the group. Okay. So basically, the algebra essentially deals with infinitesimal changes or infinitesimal elements which are very close to the identity and asks, okay, what structure does that have? And there you get an algebra. Here you get things which can add or subtract. Okay. So basically, Lie groups and so group theory in general contains all kinds of groups. Lie groups come with their own algebra structure. So understanding the algebra helps you understand the group. The algebra is easier to deal with in many senses because you can add, subtract as well. Well, one of the things I'm going to show you today, the basics of representation theory, is basically trying to, in a way, it's essentially trying to change groups which are abstract objects, things we have talked about today, into matrices, which you can add, subtract, and do calculations with. So just like being able to change abstract group elements into matrices gives you some extra power where you can use the full power of linear algebra. Similarly, being able to change, and this Lie group Lie algebra connection is even bigger because knowing what happens very close to the identity essentially tells you what happens everywhere. So if you want to understand all rotations, all you need to do is understand rotations which are very close to no rotation at all. Of course, if you don't rotate at all, you will get the identity transformation, right? Anything that you do with no rotations is identity, you do nothing. But if you rotate by a very tiny amount, that will be described by an operator which is very close to the identity but slightly different. And this slightly different thing is basically, this slightly different thing is what you call angular momentum. So all this, the entire angular momentum algebra, the commutation rules, etc., these are really nothing but consequences of the fact that rotations don't commute. By the way, I'm pretty sure many of you have wondered why, when you first encountered spin, for example, why does spin have to have the same commutation relation as orbital angular momentum, right? Orbital angular momentum L1, L2 is IH cross L3, that's sort of easy to show, right? But S1, S2 is also IH cross S3. That seems like something which you force. And you say, okay, you have the same commutation relation, you call it angular momentum. The answer really is that no matter what your system is, if you rotate by a very tiny amount, you will essentially have the identity operator plus a small correction. And the small correction will be some operator into the small angle by which you're rotating. And that will be your so-called generator of rotation for that particular system. And the fact that the generators of rotation are operators which do not commute, if they do not commute in a very specific manner, that is, LXLY has to be IH cross LZ, does not really have to follow from XPY minus YPX. It follows simply from the fact that rotations about different axes do not commute. It's a result from the geometry of rotations. Okay. So basically, that's the power of Lie algebra. That is, you are looking at small changes about the origin, and from that you're trying to figure out everything about what the group can do. And this is one reason why Lie groups are very complicated objects, but they're easy enough to study because of this. Okay, Shunjit Dash has this question. My question regarding partition and equivalence relation. Okay, is that a question or is that a comment? I couldn't make out a question.
Sir, this is a comment from my side, sir. So I get a different flavor from your lecture today, and I was appreciating that part.
Okay, thank you. Thank you. Okay, so if there are no other questions.
So one more question on Lie algebra as you are talking a bit. I don't know whether it's relevant, but it's an opportunity I should ask. So when we take out the eigenvalue out and we diagonalize the whole matrix, I'm going typically inside the concepts of Lie algebra. Is it the equilibrium state we have attained of the vibration?
This is okay, unfortunately, this is a question which I cannot really answer because you're talking about a very specific thing that you do in a very specific situation. Are you talking about, so unless I understand the context, it's difficult for me to answer this. So are you saying that are you looking at the Kartasov algebra by any chance? Or
yes,
something like that?
Yes, sir.
So you're saying that there is a Kartasov algebra which, well, actually, look, this is again not really very surprising. Basic quantum mechanics teaches you a lot about what you can do with Lie algebras. What you did, if you learned a bit about Lie algebras, you learned that you can define ladder operators, right?
Yes, sir.
Just like you did in angular momentum, the same idea, but you can have more ladder operators. But what are ladder operators? Ladder operators, things which essentially look like this. Okay, let me just go back to the. So just to remind everybody else, in angular momentum, you have this, right? In a general Lie algebra, you might have a situation that you have operators H1, H2, say H3, maybe HR, all of which commute with each other. That is, I'm writing this. So this is called the Kartasov algebra. So you have, so those of you who do not know any Lie algebra, just think about this as some set of operators. And they have a commutator which, so H1, H2, H3, HR all commute with themselves, and there are other elements which do not commute. And then you are looking at things like this. H1, E1 is alpha 1, E1. H2, E2, H2, E1 is alpha 2, E1, and so on. So what you are really saying, this is really looking very much like the fact that operators which commute have simultaneous eigenvectors, right? If you could somehow think of this as some operator acting on E1 instead of some operator commuting with E1, this would be that operator acting on E1 gives you a multiple of E1. That operator, another operator here acting on E1 gives you a multiple of E1 again. So basically E1 is a simultaneous eigenvector of all these operators. And actually there is such an operator. It's an operator which acts on operators. So it's a higher dimensional thing. So add H, for every H there's an add H, and add H acts on, the definition is add H is defined to be this. What is an operator, by the way? Anybody? What do you define? What do you mean by an operator? In a standard quantum mechanical sense, what is an operator?
That can give you some product. If you
what is an operator in ordinary quantum mechanics? Product comes later, but what is an operator?
Something that takes vectors to vectors.
Something which takes vectors to vectors, right? That's good. Vectors here, in the quantum mechanical sense, vectors could be state vectors, but in general, something which takes vectors to vectors is an operator. But the set of all operators, they are also vectors, right? Do you understand that point? Operators can be linearly combined with each other. That is, you can define E1 plus alpha 1 E1 plus alpha 2 E2 to be another operator, right? They have done that all the time.
Sir.
And so operators have a linear vector space structure of their own. So you can have, so there is a space of operators in which the operators themselves are vectors. And in that space, on that space, this add H is an operator which is acting on a vector E to give a new vector H comma E. But in this space, the vectors are the operators themselves. And it just so happens, and this is trivial really, that you can show that add H1 and add H2 commute. So what you're really asking here is this: add H1 acting on E1 is alpha 1 E1. Add H2 acting on E1 is alpha 2 E1 and so on. So E1 is really a simultaneous eigenvector of commuting operators add H1, add H2, add H3. These are called adjoint operators, which essentially is commutation again. And so all here we are doing here are finding simultaneous eigenvectors of H1, H2, H3 and so on. Not this H1, H2, H3, but add H1, add H2, add H3. We are trying to find out operators whose commutators with H1, E1, H1, H2, H3 are multiples of themselves. Just like J plus is an operator who's commutated with J3, and here there's only J3. There's only one operator which commutes with itself. J1, J2, among J1, J2, J3, right? So you just start with J3, J1 is IJ2, J3, J2 is I minus IJ1. These are not eigenvalue equations in our sense, that is, these are not, on the right hand side you don't get the same operator that was sitting on this side. But then you realize that if you multiply this by I and add it to it, you'll get J3, J1 plus IJ2 will be plus J1 plus IJ2, which is an eigenvalue equation in the sense which I just stated. So basically, what you have is simultaneous diagonalization of these commutation rules. And that's what gives you the roots and weights, which you must have studied if you're asking this question. This is, of course, an advanced thing for now, because we are going to try to talk about this near the end of the 5th lecture if I get enough time. Okay, I will have to talk about this, so I will perhaps cut down some of the stuff in between. And some of the proofs in between. Yeah. Anything else? Sir. If not, I think I should really give the organizers a break now.
Sorry? No, I'm there.
So you're here.
The interaction continues. But you are talking continuously for like quite a long time. I think we can stop today.
Look, the only reason why I'm a teacher is that I liked hearing my own voice. Right? That's why anybody
okay, so
anyway, I think we have had enough for today. Otherwise, people are going to get tired and not show up tomorrow at all.
They will run away, and then they will not show up for tomorrow.
Yeah.
So I just wish that all of us assemble here again at 7:30 p.m. Indian Standard Time. And
okay, somebody has asked for some problems. I will try, but I don't have the time to create problems, a good problem set in between. Unfortunately, my last course which I gave on group theory was a long time ago, so I don't have the problems from that.
Yeah, actually, if there is a problem, that may be useful for people.
Okay, I will try to give some problems. I did mention some of the unproven things in between, which could very well be problems, but still, I will try to create some problems. But maybe it will take some time. Maybe it will take till the end of the workshop. I will not be able to do it now. Yeah. And then after my courses, class lectures over, I will try to make some and send it over to you, so you can share.